Can folks in the chat hear me?
Yep.
Okay, so as always, remember the seating survey, section 4 today, ILC 118. Upcoming dates, Friday, tomorrow, homework 7 is due, 3 parts to it. Sunday is the usual Piazza cutoff. Next week is going to be exam number 2. It'll be released on Thursday, due on Sunday like it was last time. So there is a Piazza post up now, the what we know so far on midterm exam number 2. I will keep that updated as we get more information in for it. There are formula sheets for both exam 1 and exam 2 available on Blackboard. And I posted earlier this week a spreadsheet that does kinetic simulations for you and a tutorial video to YouTube that takes you through both how to use Excel for calculations in general and specifically how to use it with respect to this simulation spreadsheet. This is a practice spreadsheet for you to use to get used to dealing with the kinds of data you're going to be seeing on the exam. I will be posting the actual exam version of it at a future point. I think I may give it to you before the actual exam time frame becomes available, but I have to check it out this weekend, make sure that it's set up how I want it to be set up. Are there any logistical questions before we get into content today? Okay, so I found for some reason on Piazza that there was this block of live Q&A questions that I had missed basically Monday through yesterday, and I don't know why I had missed those. Most of those questions were on kinetics stuff. I put a few of them down here, and then I realized, well, there are a lot of them, and I think most people right now are working on the equilibrium stuff. So what I'm going to do is go through the equilibrium questions that are on Piazza first, talk about those, and then I will go back to either the kinetics ones that I have listed here or pull up Piazza and go over some more as the people that are here and in the chat want me to. If there are questions there that you guys aren't interested in, you're the ones that are actually here paying attention, and so I will go through and answer the questions that you guys want me to. The ones that I ended up missing for some reason, I'm going to, and if we don't deal with them here, I will go and answer them in written form on Piazza. Okay, so let's talk about some equilibrium stuff. So first of all, it sounds like there are a lot of people that are having some general issues trying to understand Le Chatelier's principle. So let's talk about that in sort of a general sense, and then we'll look at some specific types of examples with it. So Le Chatelier basically says if we have an equilibrium, so reactants, products, and if we do something to the equilibrium so that we add a stress to it in some way, a disturbance to it in some way, that disturbance is going to be more on one side than the other. It could be that you're adding some of the product to the reaction mixture. It could be one of any of several other things that happen, and we'll go through examples of them in a moment. But let's suppose that we add something to the product side. Le Chatelier very simply says the equilibrium will shift to reduce the effect of the thing you added, of the disturbance you made. That's all Le Chatelier's principle is. It says you introduce a disturbance, the equilibrium shifts in a manner that reduces the disturbance. If you think about that in terms of the equilibrium constant, so remember that the equilibrium constant is structured such that it is products over reactants. under equilibrium conditions. And remember as well that Q is the same thing as the equilibrium constant. Q is the reaction quotient, except that we do not have the assumption that we are at equilibrium in that situation. So in this situation here, where we have reactants in equilibrium with products, and we have supposed that we have added some product to the system, that means that we're adding something to the numerator. That means that our Q now has something bigger than it should on that side. So in order for Q to return to equilibrium, the numerator has to get smaller, which means that the reaction has to shift towards reactants away from products. Does that general idea make some sense as to what is being meant by this shift based on a perturbation? So whatever you do to the reaction quotient to make it different from the equilibrium constant, to get to the equilibrium constant, the numerator and the denominator have to shift in a way that reduces what you have, the perturbation that you've put into it. Now, this is in terms of concentrations or pressures, or partial pressures. It can be, this Le Chatelier's principle affects more than just concentrations. So if this were an exothermic reaction, what does exothermic mean? There's heat involved, yes, but is it releasing heat or is it absorbing heat? Releasing heat.
System.
Which means that we can think of the heat as being a product of the reaction, right? If it's releasing heat, we can think of it as something that is produced as the reaction happens. Now, what this suggests is that if we then take an equilibrium and we then increase the temperature, we can think of increasing the temperature as us perturbing the system by adding extra heat. And so when we do that, Le Chatelier says the equilibrium will shift towards the reactants. Now in this case, it's for a slightly different reason, because the equilibrium constant itself depends on temperature. So remember that when we first wrote the equilibrium constant, we wrote it as the ratio of the forward rate constant over the reverse rate constant. You remember that? Okay. And each rate constant follows the Arrhenius equation. So it has an activation energy in it, and it has a temperature in it. So the forward rate constant and the reverse rate constant depend on temperature. So when we change the temperature, we get a different value for our equilibrium constant because it's made up of these rate constants. But the idea of Le Chatelier's principle that if we perturb the system by adding heat, then the reaction will shift in the direction that minimizes that effect still applies. So that tells us something about how even the rate constants end up working. We could go into a derivation of that, looking at which one has a higher activation energy and thus has, and why the reaction is spontaneous, not spontaneous, why the reaction is exothermic or endothermic, but I'm not going to be holding you responsible for going through that analysis. So, so I'm just going to say right now, unless somebody really wants me to go into it, that the effect is that if we think of heat as being a product in an exothermic reaction, or if we think of it being a reactant in an endothermic reaction, then the prediction by Le Chatelier's principle is exactly what we would expect. Okay. Any questions on that aspect of Le Chatelier's principle? I am going to go into a specific example in a moment, talking about changing volumes in a gas phase reaction. So we'll look at that specific example in a minute. But before we get to that, are there any questions on the general idea behind Le Chatelier's principle and its relationship to heat? Okay, no questions on that. All right, so there is a specific question from Newton, I believe, that talked about an equilibrium between 2NO2 in equilibrium with N2O4, and these are gases. And the question was, if we change the volume, what happens to the reaction? So the picture we should have is that we have some kind of container. You can usually think of it as being like a piston. And we have this reaction going on inside here. So there's NO2 in there, gas, and there's N2O4 in there as a gas. And we have an equilibrium constant, which we are going to express in pressures here because we're dealing with gases. What is going to be our expression for this equilibrium constant? What is going to be our expression for the equilibrium constant? Not in terms of the rates. So thank you for getting me to clarify that. In terms of partial pressures. So we've done a lot of examples in terms of concentrations. We can do it in terms of pressures just like concentrations because they're related to each other by 1/RT. So if we were doing concentrations, what would we write? Those would be the rate constants. So in terms of concentrations, what would we do? Maybe we ought to back up and go through that part. That's fine. So I am going to take a step back to kinetics for just a moment because there's a skill we learned in kinetics that is going to apply to writing an equilibrium constant. So let's take a look at this. Suppose we have an arbitrary reaction, A plus B plus C goes to products with a rate constant K. If we know this is an elementary reaction, you should be able to look at this and immediately write down what the differential rate law is. What would the differential rate law look like here? I have to put the K in. We're going to have to do something with each of these. That will be once we get to the equilibrium constant, yes. But we need the concentration of A, we're going to need the concentration of B, we're going to need the concentration of C. Is there something else that we need to do here? Maybe with the stoichiometric coefficients? Okay, so the chat says, oh, no, that's something different. So the basic idea is that if this is an elementary reaction that's involved, which means that it's referring to a collision, a single collision amongst all these things, then you just put the stoichiometric coefficients up as the reaction orders. Okay. So any reaction we write down, if I wrote down H2 plus, or 2H2 plus O2 yields 2H2O. And if we knew this was an elementary reaction, which it's not, but if you were told that it was, you would immediately write down that the rate law was K concentration of H2 squared concentration of O2. Okay. So this is a skill that you use whenever you're analyzing a reaction mechanism, because each elementary step you need to be able to write down the rate of that step. Okay. So this needs to become second nature as you start working through these, because we're building on this as a skill for things later. So what I'm trying to illustrate with this, though, is that we have a connection, an expression that connects the concentrations of all the reactants with their stoichiometric coefficients, where they become the exponents that we're dealing with. We do exactly the same thing for the equilibrium constant when we do products over reactants. So in this case, if we were doing this, I'm going to write it down here as the concentration version. If we're looking at the products using that same formulation I just described, there's only one of these N2O4s. So we would write concentration N2O4. What would we do for the reactant side? Yep, squared. Concentration of NO2 squared. So this is how you write the concentration equilibrium constant. However, we are in this case dealing with gases, and because we're going to be talking about changing volumes, it makes a little bit more sense to talk about it in terms of partial pressures. So we write this as the partial pressure of N2O4 at equilibrium over the partial pressure of NO2 at equilibrium squared. So does that process of writing down the equilibrium constant make sense? Are we good? All right. So with this in mind, let's now think about what happens if we push this plunger in and decrease the volume of the container. Okay, so we have an equilibrium that has been established. There is some pressure of N2O4 and there is some pressure of NO2. And let's suppose we half the volume. What does that do to each of the partial pressures if we half the volume? It'll double the pressure, exactly. So what this is going to do then is that we're going to multiply the numerator by 2, and we're going to multiply the denominator by 4, because this is squared. Okay? So if you double the pressure of the NO2, you're going to have the denominator go up by 4, which means that our Q, so this is now making a Q, not a K, not an equilibrium constant. Our Q is now going to be half of our K that we need. So how is the equilibrium going to shift? It's going to shift away from whatever the denominator is, because it's too big, towards the numerator, so that we get back to where we started. Okay. So which is the denominator? The denominator is the reactants. So our equilibrium is going to shift towards products. So the idea of this is that if we increase the pressure uniformly for everything by changing the volume, then we've had a bigger effect on the side of the reaction that has more moles of gas. And so Le Chatelier's principle says we will shift in the direction to reduce that effect, meaning we'll shift from the side that has more gas towards the side that has less gas. Any questions on those concepts right there? Okay. All right. So there was, we talked about that, we talked about this. So there was a specific question, I believe from Newton, that people wanted me to look at. So this is a reaction that is a gas phase reaction. So 2 moles of SO3 in equilibrium with 2 moles of SO2 and an O2. And we can do this kind of problem either in terms of concentrations or in terms of pressures. The particular problem that was copied into Piazza was listing it in terms of concentrations. And it says for us to calculate Q and determine which direction the reaction will proceed in order for it to go to equilibrium. So where do you think where do you think you would start for this kind of problem?
We start where we did the last problem, right here.
So we could do it in terms of partial pressures, or we can do it as it's written here in terms of concentrations. And since the equilibrium constant is given in terms of concentrations, let's just leave it in concentrations. So that'll make it a little bit easier. So when you have an equilibrium, one of the first things you should do is write down your expression for the equilibrium constant. So it's almost always going to be a fraction. So I'm going to go ahead and put the fraction line. What are we going to put in the numerator? A little louder? The products, okay. So I'll put an SO2. I'll put an O2. What else do I need to do to the numerator? Yes? Add an exponent to the SO2, make it squared, because we have a 2 right here. Right. And it's also important to remember that these are the concentrations at equilibrium. Okay? It'll be a Q if it is a reaction quotient if it's not at equilibrium. What are we going to put in the denominator? The reactants, right? So SO3, are we done? No? What do we do? Square it, exactly. Okay, so this is our equilibrium expression. We have numbers for our current values. So let's see what we have. So we plug in 0.12. So for our Q, it's going to be 0.12 molar squared times 0.04 molar over 0.28 molar squared. All right, calculator. 0.12. Oh, come on, phone, switch to the scientific calculator.
It's in the chat.
Okay, yeah, I'll take a look at those in just 1 second. All right, squared. No, that was cubed. I can't type apparently. 0.12 squared times 0.04 divided by 0.28 divided by 0.28. So I got, and this agrees with what the chat came up with, 0.00735 molar. And so if we compare this number for Q to the number for the equilibrium constant that we have here, is our Q too large or too small? too small. So to make it bigger, we need to increase the numerator or decrease the denominator. The numerator is the products side. So that means our reaction is going to shift towards the product side in order to approach equilibrium. Okay. Let's see, so there's some questions here. Would this change the equation or does this show how it shifts? Not sure I'm understanding. Are we talking, is this back on the earlier thing where we were talking about the volumes? Volume changes, okay. So when we change the volumes, it does not change the equilibrium constant. But it does change the values of the partial pressures that were input. And so that's why we got shifted away from equilibrium in that situation. Okay. All right, any questions on how to think about this kind of problem? The general strategy should be if you have your balanced reaction, balanced equilibrium reaction, and you know you're doing an equilibrium problem, one of the first things you should do is write down what is my expression for the equilibrium constant. Okay? And then you look at, if you have conditions that are not at equilibrium, you look at where you are in terms of a Q relative to that equilibrium constant. Yes?
Okay, can you please explain one more time which direction we shifts and what?
Can I explain again which what?
Which direction it shifts?
Which direction it shifts, yes. So this expression here describes equilibrium. This expression here describes where we are, okay? And so this number being smaller than this number means that in our expression, we need to shift some stuff from the denominator to the numerator, okay, in order to make the number bigger so we can approach the equilibrium constant. If we're shifting from denominator to numerator, then we are shifting from reactants to products because products are always in the numerator, reactants are always in the denominator. Does that make sense? Okay. And in the chat, they're asking Q is less than K. Yes, that is correct. Q is less than K. And I typically find that when I'm comparing a Q to a K, it's just pretend that the denominators are going to be equal and think about the numerators. That way you don't have to be doing any kind of mental gymnastics with it. So if the Q is too small, then you need more numerator, which means more product. Okay. Anything clarifying on any of this? Okay. All right, so in a nice table, how do you know which side to put the minus x in? Okay, so this is something that has been coming up in each of the class periods this week. And so clearly it is a consistent point of confusion, so let's try to see if we can do something to help with that. Initial change equilibrium. So what example do we want to do? Let's just start with the auto-ionization of water. Okay, and if we're trying to figure out how much we have, and we are told that this one has a special name, Kw, and this is 10 to the negative 14th molar squared. So the first thing to do in determining what do you put in these is if you're starting with something at 0, then you can't have a negative. So if we put a negative x here, then that would be implying that we're going to get a negative concentration when we add the initial to the change lines. And that doesn't make physical sense. So in this case, it's got to be positive x in this case. So that's the first thing you should look at. The second thing would be, let's suppose we have some other situation, A in equilibrium with B plus C, and let's suppose all of them matter in this case. Okay, and we have 0.01, 0.01, 0.01, just to have some numbers to play with. And you're told what the equilibrium constant is. Now, let us suppose that the equilibrium constant we get is like 10 to the 8th molar. So that's a big number, right? Now, what is the what's the general pattern for an equilibrium constant? What over what? Products over reactants. Yep. Products over reactants, exactly. So that means that at equilibrium, we should have a lot more product than we have reactant. Here, we've got about the same. So that means that we're going to lose some A and we're going to add some B and C as the reaction goes across. If, on the other hand, this were 10 to the minus 8, it would be the exact opposite. It would be that, wow, we must have a huge denominator and a small numerator, so it's going to be reactant favored, and so we would swap our signs on here. So, and then, if we look at the last example from the ICE tables video where we had a shifted initial set of conditions, in that particular case, we made the assumption that we were going to move, we were going to have all of the reaction happen fully and then let the equilibrium back off from that assumption. So in that case, you have artificially created a case where you're starting out with a 0 somewhere, and that determines which way the reaction is going to shift. Now, given how many questions people have been bringing up about this, I get the feeling that a lot of people are worried about it. What if I don't recognize which direction it's supposed to go? And the real answer to that is, if you make a mistake and get the signs wrong on that, it's not going to matter. Because you'll solve the equations that come out of it at the end, and the value of x that you will get will end up being negative. Which is great, because then that tells you, whoops, I went the wrong way. And then you don't have to resolve it. You don't have to go back, switch your numbers, your variables, so that now I'm putting the sign correctly. No, just use the negative and say, if you had said, okay, how much is the reaction shifting this way, and you get a negative answer, then you say, well, that means it's shifting that way, that amount. That's all that means. The one thing you have to keep in mind when you do that is checking to make sure that none of the final concentrations you get are negative. That will exclude the answers that don't make sense. Because almost always you're going to get a polynomial that you're solving at this, from this thing. And so you'll have multiple solutions if it's not just a first order kind of problem. And so if you have multiple solutions, in almost every case that I've ever seen, I think in every case I've ever seen, all but one of them will give either imaginary or negative concentrations. And so that one that doesn't has to be the right answer. Okay. Question. If it was reactant over product, would the products both be negative x? Would the products both be, oh, I understand, yes. So if this were -8, then this would be plus and both of those would be negative. Is that the question you were asking? Okay, right. So yes. So the idea here is that let's think about what X means. X means how much of the reaction happens. And the stoichiometry tells us how the different components relate to each other. So if it's going this way, then for every A that is produced, you destroy one B and one C, and that's straight from the reaction stoichiometry that you have here. If it were A plus B plus 2C, then it would be minus 2C here. Okay. All right. There's another question. Will you repeat which way the reaction will move to reach equilibrium for A goes to B plus C and why? Okay. So in this case, what we were doing was saying, we look at our current, our initial conditions, and we see that's about the same amount on both sides. We look at our equilibrium constant and say, that's either huge or it's tiny. And so if it's huge, then that means that because an equilibrium constant is products over reactants, if it's huge, then that means you have lots of product. So the reaction is going to shift this direction. If it's tiny, like the one I have written here, then that means that the products are small compared to the reactants, and so the reaction is going to go this way. Okay. Any clarifications on this stuff, ICE tables in general? ICE tables are going to become your friend for the next several weeks. They're very, very common and very, very useful things for probably the next 3 weeks of material. Okay. There's also a question, it looks like a couple of people asked about, and apparently from Newton, about types of equilibrium. And it wasn't very clear what people were asking about on that. So I dug into Newton a little bit, and it looks like they're just talking about homogeneous equilibrium versus heterogeneous equilibrium. The thing to remember about homogeneous and heterogeneous is just what the words themselves mean. Homogeneous means one phase. Heterogeneous means more than one phase. And that's it. That's what the two words mean. So if you talk about homogeneous catalysis versus heterogeneous catalysis, one phase versus more than one phase. If you talk about homogeneous or heterogeneous equilibrium, one phase or more than one phase. That's just what, it's just having to do with what the words mean. So homogeneous equilibrium would be something like this, where everything is in water. And in fact, one of them is water, okay? So everything's in water. Heterogeneous equilibrium would be something like NaCl solid in equilibrium with Na plus aqueous plus Cl minus aqueous, where you have two different phases, two or more different phases involved. So that's all it's talking about. Okay, is it possible to make a bunch of practice problems with ICE tables? Absolutely, we can do that. I'll tell you that there are some ways that you can kind of easily make some for yourself, but I will absolutely come up with some as well. One thing I would recommend is going and looking up on the internet a table of solubility products. So this means the KSP, the equilibrium constant for the equilibrium of a solid with its dissolved ions. So you'll find a table with a bunch of different salts. So NaCl, Na2O. You'll find, what's a good one? Al, to SO43, something like this. In each of these cases, you'll have a number that is the solubility product. All you do to determine the reaction is to say, all right, this is a solid. What are the ions it breaks into? You have this, what ions it breaks into. You can now write the equilibrium constant expression for it. And you can then go through and calculate what are these concentrations when it's in equilibrium. So that is a really sort of quick way to build yourself some problems. And in fact, I put these here deliberately in this order because this is the easiest one because it's a 1-to-1 ratio of these two. This one you have a 2-to-1 ratio. And this one, you've got a 2-to-3 ratio. So it's kind of building in some increased complexity as you move through these. But it's pretty simple to then say, okay, at saturation, what are the concentrations of each of these? Now let's say I have it at saturation and then I add in some of this. How will the equilibrium shift and go the other direction as some of it precipitates out? So it's relatively, I'm happy to post some practice problems, but if you don't find that I'm posting enough of them, it's very easy to come up with some yourself to try. Okay, I think that was it on the equilibrium muddiest points that people had posted. Anybody have anything else on equilibrium you'd like to chat about before I try to figure out if we're going to do any kinetic stuff or talk about anything else? Okay, so as I mentioned at the beginning of class, there was this whole group of kinetics Piazza questions that somehow got lost and have now reappeared. And so I can start going through those if you guys would like me to, or we can select which ones we look at based on who's here and who's interested, or talk about anything. Does anybody have any preferences you want to express?
The catalyst lowering activation energy seems fun.
It seems like a fun one. Catalyst lowering activation energy, sure. Happy to talk about that. So here is the picture that we're usually drawn is that we have our energy and our reaction coordinate, and we have our activation barrier, and we have some temperature where we have some fraction of the molecules or some fraction of the collisions are able to get over the reaction barrier into products. And the idea is that with a catalyst, it lowers the activation barrier so that a larger fraction of the molecules successfully have enough energy to get over the activation barrier, and thus the reaction is now sped up. That's the general idea. Now, this is a simplified picture because in reality, what is happening is that it's not the same reaction coordinate in these two cases. It is actually a different mechanism. It's a different series of steps. And so typically what this will look like instead will be something with individual activation energies going across multiple steps. We're not going to get into the details of mapping out an entire process like that, but the general idea is that in this alternate pathway, the biggest barrier that you have to get over is lower than the biggest barrier you have without the catalyst present. And so because of that, a larger fraction of the molecules at a given temperature have enough energy to be able to get over the activation barrier. And that aspect is why a catalyst speeds up the reaction. It's because more of the collisions, quote unquote, are successful. Yes.
Could you touch on how catalyst is used and then like the intermediates or whatever the exact word is?
Sure, yeah. So touch on how catalysts are used and then intermediates and those sorts of things. So a lot of the catalyst problems we've looked at have been homogeneous catalysis. So I'm gonna switch and look at a heterogeneous catalysis example to give you guys some exposure to another another approach. So what I'm going to look at is the reaction of carbon monoxide as a gas plus O2 as a gas, two of those, to give 2CO2 as a gas. So this is a reaction that, that can happen without the presence of a catalyst, but it has a pretty high activation energy. You have to be at combustion engine temperatures in order for this to happen. We would, from a technological perspective, we would very much like to have the exhaust from our cars not have carbon monoxide in it because it's poisonous, which is why we have this thing called a catalytic converter in the exhaust system of cars, which is a catalyst for this specific reaction to remove carbon monoxide and turn it into carbon dioxide. So let's see how it does that. So the idea is we have a surface of an active metal. The surface, and so this is usually platinum, palladium, or rhodium. Rhodium, that's RD, I think. I'm not an inorganic chemist, so I don't always remember, but rhodium. And what happens is that these molecules are passing over it, and they will then adsorb to the surface and sort of stick. And then we have a carbon monoxide that comes to the surface and sticks. And then while it's on the surface, the electrons part of this bond come over and form a bond there to make the CO2, leaving behind just a bare oxygen. This can leave. And then another carbon monoxide can come in and take that last oxygen off and take it on its way. Now, this is a harder reaction to write as a mechanism because how do we represent the surface, right? That's kind of a little bit harder to do. I mean, we can do it. We could say that CO gas goes to CO adsorbed. We could say O2 gas goes to O2 adsorbed. We can say CO adsorbed plus O2 adsorbed goes to CO2 gas plus O. And then you can see you could add further steps so that the O reacts with the CO adsorbed and things like that to write out the mechanism. You could even write it in a way where this is saying platinum solid plus that creates the adsorbed. Platinum solid plus that yields the adsorbed version. And then when something leaves as the gas, then you're getting back a bare piece of platinum. So that's an example mechanism where the catalyst the catalyst mechanism has a much lower activation energy, so it can happen at close to room temperature. It can even happen in at temperatures like you have in winter time as well. The Platinum itself here in this case is a catalyst because if you look at the overall reaction, platinum doesn't appear in it. It is used and then it's regenerated, which is what makes it a catalyst. Now, you brought up, okay, how's this different from an intermediate? Well, in this case, these adsorbed versions of carbon monoxide and oxygen would be intermediates because those adsorbed versions as well don't appear in this overall mechanism. But you don't need them to begin with, unlike the catalyst. These are formed by the early steps and then are later destroyed so that they go away and you're not left with any at the end. So that's the distinction between a catalyst and an intermediate. Okay, any clarifying questions on those concepts? Okay. All right. So there were those questions, and I could also pull up Piazza and look up other questions that were on there. I think there were about 8 or 10 of them on there. If you'd like me to. Let me see. Let's see. Let's do a, whoops, wrong one. This one to screen share. Okay, we'll switch here. And so there were some, let me go to live Q&A. So there's a question here about the difference between an intermediate and an activated complex. Do people feel like they know what an activated complex is? Okay, this is another word for a transition state. So you remember this, this is so hard to switch back and forth between screens and document cameras. Okay, so this plot right here, reactants, products, transition state. So transition state is the configuration of the reactants and product, or the reactants that's kind of halfway between reactants and products, that it corresponds to the maximum of energy, the activation energy that the reaction has to get over. And so that is another word for that is activated complex. And so the distinction that's being made there in the question, what's the difference between an intermediate and an activated complex? The activated complex is in a specific single step, and it is the configuration it passes through very, very briefly on its way to products. An intermediate is actually a separate species that is stable for a short period before it then runs into something else to go cause a reaction to happen. So an intermediate is going to be at a local minimum of energy, so it's going to kind of sit there. Whereas an activated complex is this thing that you just briefly hit on your way through to cause a product. Okay, we have an example here of equilibrium concentrations. So I could do this example if people want. So I'm seeing some nods. Sure, I can do that. So we have a KC 4.7. So I'm going to write this separately, and then we'll switch. A plus B equilibrium with C plus D. Initial concentration of A is 0. Initial concentration of B is 0. Initial concentration of C is 1.6 molar. Initial concentration of D is 1.6 molar, and our Kc equals 4.7. And so we want to know the equilibrium concentration of A. So, camera. So that is the problem statement. So the first thing to do, in this case, we are going to have a shifting of equilibrium. So an ice table probably makes the most sense. So we're going to do A plus B equilibrium with C plus D. We are given 0, 0, 1.6, 1.6. And so now, which side should have the positive x's and which side should have the negative x's? The reactant should have negative x's, which would mean that we take 0 minus x gives us a negative concentration. So if we're starting at 0, we have to go up. So then these become negative. So we have x, x, 1.6 minus x, 1.6 minus x. Oh, see if I can write correctly. Okay, now, what's our next step? Yep. Say it again. We could find a Q, and then that would confirm for us that it's going to be shifting to the left. But if we think about that, the Q is going to be the concentrations of these divided by the concentrations of these. What happens when we divide by 0? Got a problem. So we're going to skip the making a Q part, and we're going to go straight with the equilibrium condition here. So the first thing you should do in most of these problems is write your expression for the equilibrium constant. What's that expression going to look like? Yes? Yep, concentration of C, concentration of D, over concentration A, concentration B. Okay. Well, we have values for these at equilibrium. So 1.6 minus x for both C and D, so that's going to be squared, over x squared. And we know that this is equal to, we're told up here, 4.7. So 4.7x squared equals 1.6 squared. What is that? So 2.56 minus 3.2x plus x squared. We simplify 3.7x squared plus 3.2x minus 2.56 equals 0. And at this point, we have a quadratic equation, so we use the quadratic formula. So x equals negative b, or no, excuse me, equals b squared. No, I'm doing this. I know this. Okay. All right, negative b plus and minus the square root, b squared minus 4ac, all over 2a. So that's a, that's b, that's c. Or you can go to a quadratic formula. formula calculator. So coming here, we have A is A is 3.7. B is 3.2. And C is negative 2.56. We know that it can't be the negative one because that would give us negative concentrations. So our answer has to be X equals 0.505. And so we can see that that value is in fact our concentration of A, which we were asked about. And then if we wanted the concentrations of C and D, we would take 1.6 minus 0.505. So this would be one of those examples where making the approximations that the change is small would not work, because we see that it's changing by about a third of the amount. So why did we use the quadratic formula? So when we look at this equation right here, it's a coefficient times x squared plus a coefficient times x plus a constant. So that is a quadratic equation. And so to solve that, we use the quadratic formula. Quadratic just means a second order polynomial, meaning that the highest power of x is 2. And Shane's exactly right. Solving by factoring would take forever to figure out. Yeah, and solving quadratics by factoring is, once you're dealing with decimals, is just a nightmare, not even worth the time. Okay, we have about 7 or 8 minutes left. If somebody has anything specific you'd like me to do, that's fine. I'm happy to switch back to Piazza and see what other questions are up. So let's see. So if you're told that something is 0 order, if it's 0 order with respect to all of them, I would assume so based on how it's stated. Let's see. How do you determine the frequency factor within the Arrhenius equation? So that's the A, the pre-exponential in the expression. That's not something that you can just calculate. That is something that either you would be given or you would want to figure it out. Honestly, if you're trying to figure it out, I don't know that you need it very much. It's the activation energy that's the more important quantity, because there's an energy interpretation of it. The frequency factor doesn't have as much information that's as immediately useful. So it's something that has to be there to make the rate constants the right magnitude and the right units. But it's not something that we're going to go very deeply into. More confusion over catalysts versus intermediates. Catalysts, that's an interesting question, actually. Could catalysts be an intermediate, or will a catalyst always be something that is introduced from an outside source? My first instinct is to say it's always something that's introduced based on what we've already talked about. But there is a phenomenon known as autocatalysis, where a product that you form actually speeds up the process, speeds up the reaction. And so the product that you form ends up acting as a catalyst. So I think it's a little bit vaguer than any of us would really like. So generally, when we talk about a catalyst, the most common situation is that it is something that is introduced externally from an outside source. Let's see. So how common are unimolecular reactions? Pretty common, quite a bit. And yes, the rate is going to be just first order, because unimolecular, anytime you've got unimolecular, bimolecular, termolecular, any of those things, that means you were talking about an elementary step. And so you can write the differential rate law straight from the reaction stoichiometry. This was an interesting one. In a collision theory lecture, it said that activation energy and kinetic energy acquires their energy from temperature. And so can activation energy and kinetic energy be used interchangeably? And then how does temperature affect them? So this is a pretty good one question for trying to understand these reaction coordinate diagrams. So strictly speaking, the plot that's shown here is potential energy. So reactant, product. The activation energy isn't an amount of energy that you have. It's the size of the energy barrier you have to overcome. A given collision will have a certain amount of total energy. Some of that will be potential energy, this amount here, and some of it will be kinetic energy. As the reaction proceeds and you start heading up this hill, the kinetic energy that you have gets converted into potential energy until you get to this point here, where everything is potential energy and there is no kinetic energy. At that point, you don't have any kinetic energy to keep going up the hill, so the reaction turns around and it's a failed reaction. If, however, you start with enough kinetic energy and are up here, then this is how much kinetic energy you have. You still have potential energy down here. As you go towards the barrier, you still lose kinetic energy to potential energy, but when you reach the transition state at the top, you still have a little bit of kinetic energy. And so at that point, you're able to get over the barrier and go on to reactions. So there are only two kinds of energy, potential energy and kinetic energy. The sum of the two is a constant, the total energy of the system. When you change where you are on one of these plots, you are changing the distribution of the energy between kinetic energy and potential energy. So as the potential energy goes up, the kinetic energy goes down. The activation energy isn't an amount of energy you have, it is a size of the hill you have to get over. Okay. Anybody have any further confusions on activation energy, Arrhenius equation, how these energies interact? Oh, I just did that whole thing to you. I didn't have the dot cam on for either the chat or for either the chat or the screen, the class. I could go through that again if people want me to, but if you feel like you know it, that's fine. Either way, no? Okay. All right, we are pretty much out of time. Thank you all very much. Next time I do that, please yell at me.